All right, for the second part of these notes, I'm going to have you start off by trying to do exercise 3 on your own. Notice we just did the comparison test, so you're going to try to apply that to this particular series, which is 1 over square root of n squared plus 1. And I give you a hint there, so go ahead and pause the video now, try to do exercise 3, and then unpause when you're stuck or done. All right, so the first thing that I might think here is I'm going to say, like, well, look, this seems like it's really going to be like 1 over n, because n squared plus 1 is really pretty close to just n squared, and the square root of n squared is just n. So I'm going to guess that this diverges, but I'm not sure. I need to do a comparison. So if I do this comparison to try to get to that 1 over square root of n squared, what I have to do, if I'm removing a plus 1 from the bottom, that makes the denominator a little bit smaller. And if I make the denominator smaller, my overall expression gets a little bit bigger. It's definitely going to be less than, but I'll just say less than or equal to. And this, of course, is equal to the sum of 1 over n, and that's the harmonic series, which diverges. So I should be happy, except I'm not, because what I just proved is that my original series is less than something that diverges. If you're less than something that diverges, that doesn't help you. You have to be bigger than the thing that diverges in order to say that you also diverge. So this, what I just did there, it's no help. But I can use that same idea to try to find something that will work a little bit better. So let me do some rough work over here. So at first I said the square root of n squared plus 1 is greater than or equal to square root of n squared, which is equal to n. And then, when I did the reciprocal of it, I got the inequality going the other way. I could have also done this, though. The square root of n squared plus 1, that's always going to be less than or equal to what I get if I just multiply n squared by 4. Right? If I start at n equals 1, this thing's going to give me the square root of 2, and this is going to give me the square root of 4. For n equals 2, I'll get, the square root of 5. 2 squared plus 1 is 5. And here I'll be getting 4 times 4 times 4. The square root is 64. So this thing over here, the square root of 4n squared, is always going to be way bigger. And of course, that's easy to take the square root of. That's why I chose the number 4. That's always going to give me 2n. So what happens when I do the reciprocal of this? If n squared is less than or equal to 2n, then 1 over the square root of n squared plus 1 is going to be greater than or equal to 1 over 2n. Because I'm making, when I change to 2n, I'm making the denominator bigger, which is going to make my fraction smaller. So now I can do this. Sum to infinity, starting at n equals 1 of 1 over the square root of n squared plus 1. That is going to be greater than or equal to the sum to infinity, n equals 1 over 2n. But that's just 1/2 times the harmonic series. And that thing diverges. Because the harmonic series diverges, and if you take 1/2 of a divergent series, you're still divergent. It still goes to infinity. So this implies that 1 over square root of n squared plus 1 diverges by comparison. And that's because it's less than that thing right there, which diverged. And I put in this remark here that it can be difficult at first to use comparison to tell if a sequence converges or not. And the thing is, you often want to add or subtract something from your numerator or denominator to make the comparison work. But sometimes that doesn't always help. And then the next step is often to use multiplication. Because the thing is, when you use multiplication like I did up here, I end up getting this 1/2 out in front, but multiplying by a constant doesn't matter. If you're convergent and you multiply by a constant, you're still convergent. And if you're divergent and you multiply by a constant, you're still divergent. So those are sort of your two main steps to see if a sequence converges, or sorry, to use comparison. First to add or subtract something, and next to use multiplication. And there's this also fun example in the textbook if you want to check it out of using your knowledge of functions. So the last test we're going to talk about today is the limit comparison test. So often you have a feeling that a sequence will converge or diverge and have an idea of a sequence to compare it to, but you can't make the inequalities work. That's what we saw here, right? For exercise 3, we were like, it seems like it's pretty close to the harmonic series, but the inequality didn't quite work. And you can often use what's called the limit comparison test in these situations. It's kind of just an easier version of the comparison test. And the idea is if you know that one series is really like another series, then the limit comparison test is often the one you want to use. It won't always work, and we'll do an example of that in a little bit. But first, let's just define it. Suppose you have two series, A and B, and they have positive terms. If the limit as n goes to infinity of, I think I'm writing this wrong. I think it's actually just A sub n over B sub n. Yeah. Sorry, there should not be a summation there. Limit as n goes to infinity of A sub n divided by B sub n. So these are just the terms in the series. If those equal C, where C is a constant, then either both series converge or both series diverge. So once we know what one of them does, we'll know what the other one is. So you have basically a complicated series, compare it to an easy one that you know if it converges or diverges, and then you're done. So let's see how this works in example 4. So in example 4, we're just looking at some of these series that we looked at before, and we're now going to use the limit comparison test instead of just doing the straight comparison test like we did before. So for this one, we wanted to say that it's like 1 over n. So the limit comparison test for A, we would look at that and we would say, okay, let's take the limit as n goes to infinity. I think it's like 1 over n, and I'm going to compare that to 1 over square root of n squared plus 1. Well, that's the limit as n goes to infinity. I can now multiply by the reciprocal and get the square root of n squared plus 1 over n. That n on the bottom, I can rewrite as a square root of n squared, and then I can bring them both under the same square root sign and do a little bit of breaking up of that fraction, and I get n squared over n squared plus 1 over n squared. Limit as n goes to infinity of the square root of 1 plus 1 over n squared. And what happens to 1 over n squared as you go to infinity? Well, that goes to 0. So this is just going to equal the square root of 1, which is just 1, which is a constant. That's kind of nice. And I think actually I need to check my information, but I feel like this constant c should be a constant not equal to 0. Yep. Sorry, I forgot something in here. C is a constant, and we have to have c not equal to 0. That's very important. So this 1 is a non-zero constant. So that implies that both series do the same thing. And 1 over n diverges. So that implies that 1 over square root of n squared plus 1 diverges also. All right, let's try b now. So now that we got the hang of it, it's pretty easy to say like, oh, like this top thing here are some 1 plus sine n over 10 to the n. It's going to be like just 1 over 10 to the n. So let's do our limit comparison test. And we want to take the limit as n goes to infinity of 1 over 10 to the n divided by 1 plus sine of n over 10 to the n. Again, we multiply by the reciprocal, the 10 to the n's cancel out, and I get the limit as n goes to infinity of 1 over 1 plus sine of n. And the problem with this is that limit does not exist. So this sine of n is going to just bounce back and forth between -1 and 1, and it's never going to settle on any particular numerical value, right? Like this 1 plus sine n, it could be as large as like 1.99, and it could be as small as 0.01 or even smaller. It'll never go below 0, and I guess technically I don't think the sine of n would ever equal exactly 1 because pi is an irrational number, but whatever. Point being, it's going to bounce around. People often say that it oscillates is another word. The values oscillate. So I cannot use the limit comparison test. Because to have the limit comparison test work, I have to actually have this thing equaling a constant number. The limit has to exist and it has to equal a non-zero constant, and here our limit does not exist. So in this case, we had to use comparison like we did before. The limit comparison test won't work. I should mention as well, limit comparison test will work if you have something, here we had an example where we compared it to something that diverged. You can also compare it to something that converges and get that to work sometimes as well. The end.